problems much easier. So for example, we have the equation that gave us PV is equal to an nRT. Few things about this equation. The R constant is going to be given to us as 0.08206 atmospheres times liters over moles and Kelvin. When we do some problem solving with this equation, or any of the other equations, your temperature has got to be in what units, guys? Kelvin. So as we go to the problem solving, I'm going to emphasize this. But when it comes to units of pressure or volume, if you're using this equation, the R is going to decide what kind of units you need for pressure. So if it turns out that you're using this R constant, then your pressure must be with what kind of units, guys? Atmosphere. What about the volume? What kind of units do I have to use in this equation for volume? Liters. Okay. We have another equation in our problem solving that's going to come up. The other equation is given by P1 V1 over N1 T1 is equal to a P2 V2 over N2 T2. Why would I use this equation? I want to expand that within our problem solving session. And I'll give you guys a chance to work on certain problems that I've given from in the past. We'll crank up the levels of the problems. For each problem solved, each question is going to teach us something. The answers are there, but I want to have a chance to discuss some of these things with you. So when I use this equation, on the other hand, I don't care what kind of units you have for pressure, as long as they're consistent. So this could be kilopascals, but P2 better be a kilopascal also. And why would I know I'm using this equation if it's a conditional problem? And how will I know if something is conditional? This is the part that I want to make sure we understand in our steps when we work with ideal gas law problems. I've already posted a sample exam for you. And I have a whole bunch. I intentionally put a lot more ideal gas law problems in the sample exam so we get practice on this besides the homework. And the units of temperature must be in what units, guys? Kelvin, all the time. But there's more that I want to put on the board. The other part, guys, there's another equation that comes up. Or there's another R constant value. Sorry, I forgot to give you. There's another R constant value that we get, which is 62.4. And if I give you this R constant value, note that the units for pressure is millimeters mercury times liters over mole and Kelvin. And so if you use this R constant in this equation for your plug-in chart, what must be the units of pressure, guys, that you guys need to plug in? It has to be consistent with whatever the units of pressure you get in the R constant.
What are those what is the acronym that's next to the number, the constant?
Oh, you mean this?
Yeah, on both of them.
These are the units, right? So this is called mmHg, which is millimeters mercury. And I'll bring this up a little more.
mmHg.
mmHg times liters divided by moles and Kelvin. Guys, is everybody clear on the units? The question was, what is this? So it wasn't very clear. So it's mmHg, which means it's another units for pressure.
And what about the other one?
The other one, I'm using ATM, which is atmospheric units for pressure. Okay, so there's different units. I could also use torr, but these are the two different constants that you guys are going to get for pressure. I mean, R with two different units of pressure. So we have other units of pressure that comes up. But if I give you this constant, because it's millimeters mercury, then I have to have this pressure in units of millimeters mercury. And I'll emphasize that in our problem solving, because we need to beat that up in our problem solving. But I just wanted to put the equations on the table one more time. And we know where this is all derived from, right? The four laws we started, put them all together, guys, we get to these equations. There's one more equation. I'm not going to derive these. There's one more equation that says pressure times molar mass. So instead of volume, I'm going to be using molar mass is equal to density times R and T. And in this equation, instead of having volume and moles, I have information about the molar mass of the gas. Because maybe I need to find, the molar mass of an unknown gas in a problem. And this equation shows that molar mass and density of the gas for ideal situations, are directly related to each other. There goes the third equation that I want you guys to be aware of. When do I use this equation? When I go through a problem where they're measuring molar mass or density, then it's more convenient to work with this equation. So there's three different equations, guys. You could get away solving the problems with PV equals nRT, but if you don't use the correct equation, guys, with the problem solving, it could get very difficult very fast. The algebra could get heavy. So we want to eliminate that by considering all these three different equations. We know how these two are derived. And this equation is derived from PV equals nRT, which I'm really not showing. I'll have another video up where it shows the derivation. It's from my Chem 101 class. But at this point, for Chem 110, I'm just going to give the equation. Go ahead.
Professor, so when you give us the problems, all we have to recall and remember are those three formulas, but those R constants are...
I'm going to provide it to you.
Okay.
In fact, if you look at the sample exam, I also provide the PV equals nRT. But knowing these two formulas is going to help a lot with the problem solving. Right? And that's what I'm going to prove to you guys with the problem solving. How would you know which equation to use for a given question? Are we clear on what I'm trying to say? And then I'll give you a chance to work on the problems. I'll go around and we'll fix some of the details that's important, because you have to also put in the work yourself. And we'll do a little bit of that on Monday as well before we move on to the next topic, right? But over the weekend we got something to do, guys, with this, the work that must be done is with ideal gases. I know, I want you guys to enjoy your Thanksgiving, but there's also some work to be done for next week. And we have a chance to digest the food, because we have Monday and Tuesday for any questions that you may have. But there's one more thing that I want to bring to your attention. In our problem solving, there's also this thing that's going to come up that says STP. What is that? And this is all in the notes. So standard temperature and pressure. This stands for standard temperature and pressure. I said it. And the standard temperature and pressure, guys, is going to give us values for temperature. So temperature here is going to be 0 Celsius, which is 273 Kelvin. Notice that every time I get Celsius, I quickly change it to Kelvin, because in our problem solving, your temperature better be in units of what, guys? Kelvin. In the previous, before the previous exam or the quiz, I was telling you, don't just make a single bond with fluorine. Just keep it as a single bond. Fluorine acts to be single. I'm gonna, from now on, instead of saying double bond, I understand those kind of errors can come up. And for ideal gas laws, I'm gonna keep saying, please make sure that your units for temperature is in Kelvin. And you're gonna have problems, and some problems, it's tempting to keep it in Celsius, and I'm gonna project those, bring it to your attention. But you also need to, practice it yourself. So you gotta sit down and actually try to go through the problem and see if you're making those mistakes and look at the answers. Don't just look at. I've been preaching this from the beginning, guys. It's important that you work on the problem and then check the answers. We'll try that today. I like the fact that we have all this time to work on this a little bit. So what about the pressure at STP? That's going to be 1 atmosphere. I can also write that as 760 mmHg, because 1 atmosphere is 760 mmHg. Any relationships like this, I'll provide it to you. So the relationships or the equalities between different units of pressure, I'm definitely going to provide it for you. But the fact that standard temperature and pressure are these values of temperature and pressure, you got to remember. But you could ask a question and say, okay, look, how come you choose that for a standard temperature and pressure? That's beyond this class. Why do I keep that as my standard? So I can work with things with respect to that. That's a question, guys, that requires our knowledge of what it means by equilibrium and some other thermodynamical ideas, but we're not responsible for that. Are we okay with that? Just you got to remember that, at standard temperature and pressure, this is what we get for temperature and pressure.
You mean like why mercury? That's what I'm thinking.
No, this is just units. This is a way of basically measuring some parameters, right?
It doesn't have to be mercury, it could be anything. That's just what you're using.
This is one of the units for pressure. We have different units of pressure. It could be pounds per square inch, it could be atmospheres, it could be torr, and this is one of the units. It's based on the experimental technique of using mercury within a barometer to measure the pressure based on the height it ends up with pressure in the air and the so I'm sorry I didn't bring that up, but that's one of the units for pressure.
Okay.
And I want to make sure we can concentrate on the problem solving, but we have these different units of pressure. If you ever want to go from one unit to another, I promise to give you guys the conversions for it. And you'll see in the problem solving how that works. Right? Because the main thing about today's session is, let's get those problems and how do I approach. There's steps involved with this. But this information is needed to get there. And there's one more thing that comes up, guys, at STP. If I plug in this temperature and pressure in the PV equals nRT for one of the R constants, and I consider 1 mole of gas, I get an equality. And at STP, and it's true at STP, for 1 mole of gas, guys, I'm going to get 22.4 liters. At STP, for every 1 mole of gas, I get a volume that's 22.4 liters. This is useful because for some problems, for some questions, the reason this is useful, guys, because for some problems, it's going to avoid using the equations. You could use this equality to get the job done. And I want to get to those problems as well. And please do not misunderstand this statement about 1 mole is equal to 22.4 liters. Sometimes we misunderstand, and if I ask you, what's the volume at STP? I don't know. It could be anything. You can't just say, oh, the volume at STP is 22.4 liters. That's not a true statement. But I can say that for every 1 mole, I have 22.4 liters. Is everybody clear on this? At standard temperature and pressure, I only get 22.4 liters if I have 1 mole of gas, any gas, in an ideal situation. Is everybody clear on this? If I have 2 moles, then I'm going to get twice as much the volume. So when it comes to moles and volume, we take that as an equality. It's a relationship. And I get that relationship if I plug in temperature and pressure into the PV equals nRT. If you want that proof, we can talk one-on-one on that. But there goes another case, and these are the tools we're going to be using, guys, for our problem solving. Of course, we derived those equations from the 4 different laws, so you guys need to know the 4 different laws. We had a lecture on that last time. In fact, guys, this lecture, just in case you did miss that lecture, I'm also going to have a video uploaded. I'll send you guys the link. I ended up videotaping another lecture that discusses the 4 laws and what's needed as far as in theory for you guys to prepare for. Is everybody clear on this? So let's get to the problem solving. What are the questions that I ask you? How do I approach the questions? Did you guys copy everything? These are the tools we need. How do I work with the problems? Okay? First question. Let's read the question. Can you guys see the board? No? And I can see why you can't see it. It's not very deep.
No, it's the light, Professor.
The light is not. Let's so.
No,
I haven't mentioned this whole STP business. Let's take a look at this. Question number 1. What steps do we take? How do I start this question? But let's read the question first. A balloon has a volume of 785 milliliters at 21 Celsius. Okay, to start with. And then they're talking about, if the temperature drops to 0 Celsius. Right? What's the new volume of the balloon? I know, we haven't yet started working with this problem, so let's just give this a start first with a couple of examples. Right? So, I have a balloon that happens to have a certain volume. There's a temperature associated with that. And then they're telling me that the temperature changes. Guys, every time you read a question, and hear me out, and we're going to get to the bottom of this. Of course, it's important to see what's given to you. But if you're reading a question, and if in a question, one of the variable changes, is it changing in this case? Is there a variable changing?
Yes.
And when I talk about variables, are we clear about the fact that we're dealing with this volume, pressure, temperature, moles, and that's how we started kind of organizing ideal gas laws from the beginning? So if you read the question, do you realize that there is a change happening with the temperature? If you realize that there is a change happening with any one of the variables, I'm going to call that a conditional problem. I'm going to call that a conditional problem. And for this type of problems, the equation that I'm going to be using is not PV equals nRT. If you use PV equals nRT, it's going to get hard. You could get away with solving it, but that's going to take some more algebra. And so choosing the right equation for a given problem, if you guys figure out under which context is it, and use the correct equation, guys, saves a lot of time and makes the problems easier. And I'm going to prove that to you with this equation. So what's the first step? Is the question conditional or not? Can we realize that? But are we okay with this part? So I write down in the first step what I got, and let's think about the problem solving. Yeah, when it comes down to the problem solving, guys, I just gotta pick the right equation. What equation would I pick to solve for this, right? That's the question now. What kind of a question is this, Mara? Conditional or not? Conditional. I'll take your question.
Quick question is, if you are told that P is
There are no quick questions, but because I take
if you
it.
are told that P is constant, do you use 1 ATM for constant?
Say it again.
If you are told that P is constant, do you use 1 ATM? 1 atmospheres for pressure?
I don't know. It could be 2 ATMs, it could be 3 ATMs, right? That's a little too much, but yeah, I don't know. It's a constant. I have no idea what it is. And if you try to use PV equals nRT, you have no idea what the moles are, and you have no idea what the pressure is. Arne, it's okay if it's a bad handle. You don't have to hold it from here. Because it's important you also pick up the lecture, for this one. So what equation is convenient then? The conditional equation. So if you use P1 V1, P1 V1 over N1 T1 is equal to a P2 V2 over N2 T2, it's going to help us solve this question. You know what I like this equation? Because if the moles are constant, let's say the moles are 2 moles, isn't it going to be the 2 moles for N1 and N2? And if you have 2 moles for both of them, wouldn't that just cancel? Anything constant just comes out of this equation. Thank you. That confirms. Right? What else cancels in here? Pressure. Did I have to have a value for it, Murat? Did I have to know if it's 1 atmosphere or 2 atmospheres? It's not STP for me to say that it's 1 atmosphere for sure, right? It didn't say anything. And so that's all as well. And I'm left with all the variables for the plug and chug. And by the way, a side note, whose law is this? Good. Because Charles started volume versus pressure. That's another reason I like this equation, because just keep the variables that the law started and then it'll give you the expression for the law. So if you know Charles started volume versus temperature, just keep those variables from this overall equation and get rid of the others. You would go and figure out what kind of expression is Charles' expression. So you don't have to remember 4 different expressions for the laws. As long as you know what they started, you can just keep those variables in there and you get to know. And so I know this is Charles' law because of it. Is it recording? And so what else is left for me to do? Plug and chug. Plug and chug, guys, that's it. You know, I'm going to plug in all the values. And please do not plug in Celsius in any of these equations. Make sure it's in units of Kelvin, even though they're both Celsius. In fact, for this problem, you know, if you plug in 0 Celsius, that's a big problem. It's an infinity. So we're going to have 294 here, Kelvin. We have 273 Kelvin here. The Kelvins cancel. My V1 is 785 milliliters, and you might say, I thought in PV equals nRT you had to use liters for the volume. Not in this equation. Why not? In this equation, I don't care what kind of units you use for volume as long as you're consistent. So if I use milliliters, this better come out as milliliters. The units will show me that. Yeah. And so I do the math. So we do the algebra, we multiply both sides by 273. I don't like to do that. I just push it here. So if it's divided here, I make it multiplied there. So you want to also work on the algebra so you can do this as quick as possible. And what do we get for an answer?
728.9.
So the V2 becomes 728.9. What's the units? Or 0.3?
Milliliter.
Milliliters. Why? Because this was milliliters, right? So if you plug in milliliters for one of the volumes, the other volume better come out as milliliters. Do you see that? We're gonna have a video after this. You know, also take it. Emily, you saying? Guys, does everybody confirm this value? I don't know. Like I'm trusting that.
This is
So 273 times 785. I'm just doing the volume chart. Because I cross this up. It's divided here and multiplies there. Yes, Nina?
If I use the V1, T1, V2, T2, it's the same thing.
That's exactly what we use.
No, you use the over one, no?
Yes, I did the algebra after. Right? So I started with V1 over T1 is equal to V2 over T2, plugging the values, and then did the algebra.
So we only want to use the variables that we know what the values are.
Anything constant just drops out of it.
Drops
And I'll give you guys a chance to work on another question.
Are we gonna round it off to 3 sig figs, or are we still into that?
Keep it 3 6. Yeah, round it up.
So it's 729 because it's 728.9.
That's right.
So we can put 7.
But does this make sense? Does it make sense if the temperature goes down, the volume should go down? Yeah, that was part of the Charles law. That makes sense to me. You also want at the end make sense out of the value we get. Okay, let's work on another question. I just want to make sure you guys are thinking about these problems correctly. I like this question. Give this a try. Let's take a few minutes to work on this problem, guys. Just a few minutes to work on this problem, right? There goes question number 3. Actually, let me ask you. As you guys are reading this, can you read the board?
Yeah.
Right. So if you read the board, question number 3. I want to ask you, conditional or not? Just let's think about that first, right? That's something that's important for our first step. Is this conditional or not, right? How do I know? Good question. Are any of the variables changing? Do I start with one variable, end up? So in the previous problem, I started with 21 Celsius, ended up with 0 Celsius. Well, that's conditional. There's the first temperature and there's the other temperature.
Yeah, it's changing. The volume is changing.
Is it?
No.
So I got this helium gas that starts with 0.180 liters. Guys, let's think about this together. Is that okay? So and then they're saying, okay, there's a pressure of 0.8 atmosphere, so they'll give me the units. And I got a temperature of 21 Celsius, and they're saying, what will be the temperature in units of Celsius? For the helium, if the volume is now what? Okay, they don't say it that way. They're saying, at what temperature will the helium have a volume of 90 milliliters, and a pressure of 3.20 atmospheres? All right, now I'm going to come back and repeat myself again. I guess we'll make this into a part 2. Can I get everybody's attention? Marat, we're on the video. I'm glad you guys worked out this problem, and I went around, and the reason for this is to see where you guys are so we can build it up. So now I know what I need to talk about. A little bit of a problem with algebra, we'll fix it. It's not the issue, guys, but let's take the steps. What was the first step? Conditional or not?
Okay.
And write down everything that's given. How would I know if it's conditional? Hiram made a good statement earlier, guys. I know it's conditional if I got two numbers for a given variable. Do I have two numbers for volume? Yeah? They give me 0.180 liters and then they give me 90 milliliters, right? I have two different volume numbers for me. And I also have two different numbers for pressure that's given to me. So that makes it conditional for me. Thank you, Harry. Thank you very much for that statement. I'm going to use that from now on. Right? Instead of screaming the way I was screaming earlier, right? Two different values for the same variable. Makes it conditional for me. And I'm going to write that down. I'm going to write that information down. So I'm going to write everything that's given to me as conditional now. So there is 1 and 2 conditions. Start with that step. So these guys are giving me a volume of 0.180 liters. And I have a volume that's 90.0 milliliters. Because there are two different values given for the volume, I have 1 and 2 condition. That's all it takes, right, for this. So reading the question, sometimes it's hard to see that, like especially the way this is formulated or worded in this case. Right? What else do I have as 1 and 2? I have my pressure as 0.180 atmospheres, and I have another pressure value that's given to me as the second pressure, 3.0 atmospheres. Are we okay with what I'm saying? Step 1, write down everything you got. What else?
Convert your volume. I like to get rid of the decimal, so I made it.
And we'll get there, for sure.
Not yet.
You're right. I just want to point out what I saw earlier so we could fix it, just in case some of us made the same mistake. But you're right, Hayden. But there's one more thing missing. They're also giving me the temperature at the beginning,
29.
which is 29 Celsius.
Which is 302
Right.
Kelvin.
And we'll get there too. And these guys are asking me for the temperature in units of Celsius. That's what I'm looking for.
Oh, okay.
And what's a constant here? Anything not varying? Mole. How do I know that? They didn't say anything about any moles leaking. If the problem doesn't mention anything about any moles, then it's a what? It's a constant. So if you realize this thing, you're on the right track, and some of us just solved it. And this is all it takes, guys, the approach, correctly getting to the right equations. And so this is conditional. So what equation would you start with? Would you use PV equals nRT? By the way, you can. And you can try if you want. But I wouldn't. Because if you use PV equals nRT, now you have to find moles. Then you take the moles with other volumes. No. And I have to remember the R constant. You don't have to, I'll provide it for you. But it takes more energy, more time. So what equation is convenient, guys? That P1, V1 equation. And as long as I remember that equation, I'm going to write that down. P1, V1 over N1, T1 is equal to a P2, V2 over N2, T2. I know I'm using this equation for my plug and chug. But there's some things we can or cannot do with the way we plug in the variables, and I'm going to bring that to your attention. First of all, what drops out of this equation? That's why I like this equation. And I'm not naming any names. We got this whole thing by putting all the laws together, right? That's basically going to be a lecture from the previous video, I would say.
Okay.
I'm going to post another one.
We'll get rid of our ends.
Ends are all
Constant.
because it's a constant. Didn't we talk about that before? It's the same idea. Ends are out because it's a constant. Boom, it's gone. I didn't even have to have a value for it. If you had used P equals nRT, you were supposed to find a value for n, and then they take that value, unless you're really good at the algebra and you put it all together. But if you put it all together, you're going to come down to that equation anyways, which is conditional.
Can you have negative degrees in Celsius?
Yes? We have negative degrees in Fahrenheit, we have negative degrees in Celsius, and this is why we're not allowed to plug in temperature in units of Celsius, because you might get a negative value for it for temperature. If you get a negative temperature into these equations, you might get negative volume, which makes no physical sense. You either have space or you don't. So your units of temperature must be what? Kelvin.
Except when you get to the, if it wants it in Celsius, you have to then convert that Kelvin back to Celsius.
But you know why I like this question?
Because it
I have a reason, guys. I picked these questions for a reason. This is what I meant to say. It's very tempting to say that, okay, since he's asking for temperature in Celsius, can I just, now I'm going to do the plug and chug. Can I do that? Can I take everything I got and do the plug and chug?
No.
This is what I saw going around, so we want to fix it. I'm glad you guys had a chance to work on this problem. This is what I saw. For T1, that was plugged in at 29 Celsius. Right? Well, what's the problem? Before I plug in any of the variables, can I do that?
No.
But I can see the argument. I can see the argument. Now, if I plug in Celsius here, aren't you going to get Celsius for the temperature? If you use volume or pressure, I would say nothing. But we're talking about temperature, guys. Temperature has got to be plugged in units of what? Kelvin. I don't care if they're asking me to find the temperature in Celsius afterwards. I got to keep it in Kelvin all the time. Otherwise, guys, the equations are not physical, and I gave you the reasoning for why it's not physical. So you got to have your temperature in what, guys?
Kelvin.
And this is why, guys, the practice is important with this type of problems. You have it. The answers are there. This is all solved for us. It's in our sets. But you got to give it a try. You got to make that mistake and check. Oh, okay, man, I plugged it in Celsius, and so you fix it for yourself. I could be here doing a whole bunch of problems for you. It's not going to help. So I need to make sure that all my temperatures are changed to Kelvin. How would I go about doing that? Just add 273. So we're going to add 273, and Hayden, you said that turns out to be 302 Kelvin. And so when I plug in my temperature, better be in Kelvin, so that's 302 Kelvin. My pressure, can I plug in P1 as atmospheres and P2 as atmospheres? Yes, I can, as long as they're both the same units. It could have been kilopascals. I didn't have to change it to any other units. As long as they're both the same, and if it's a conditional question, I could plug them in there. Except for temperature, it's got to be Kelvin, no question about it. And so my pressure, I got this 0.8 atmospheres, and I have the pressure for these, which is 3.20 atmospheres. And then I got the volume to plug in, and if I decide to plug in liters for V1, right, then my V2 has to be in liters. If you decide to plug in milliliters for V2, then your V1 has to be also in milliliters. That's another mistake I was seeing when I was going around. Now, did you make that mistake? Let's correct it. That's the whole idea. You give this a try, and then we check, and we have a conversation about this. Right? That's the whole idea for this type of problem. So this is, now I'm going to choose to keep it in milliliters. So to keep it in milliliters, we're going to multiply it by 1,000 milliliters over 1 liter. Just to prove to you that you could also have things in milliliters. It's okay. As long as both volumes are what? Milliliters. Oh, it's a little, let me give you a little side note. If I had used PV equals nRT, are we here with that? If we use PV equals nRT, then I would have been forced to keep my volume in units of what, guys? Liters. If you use PV equals nRT, then I would have been forced to keep my volume in units of liters. But if you're using the conditional equation, as long as they're consistent, you're good enough. And so this is going to be 180 milliliters, guys, and this guy is going to be 90. And you might say, but you can't, why did you keep it in milliliters? I can, as long as they're both milliliters. Can I keep it in liters? Yes, I can, as long as they're both in liters. But if it's PV equals nRT, then R constant, the units for the R constant tells me what kind of units I could use in my equation. Are we okay with this? So the plug and chug depends on how you're using that, what equations are you using. If it's the P1 V1 over N1 T1 equals P2 V2 over N2 T2, as long as I'm consistent with the units, with one exception, temperature has got to be what, guys? Kelvin. And you can do the algebra a number of different ways. Like guys, now you're going to have to do all this cross multiplying. Some students can just multiply all the numbers first. What I like to do, if I see a variable I'm looking for, I first call that an x. Is that okay? And since it's an equality, I like to bring my x up. This is just the way I do the algebra. If you're going to flip this x up, so this is down just to separate what I have. So if I'm going to flip my x up, then I'm going to flip the other side as well. So I like doing this. And then I'll multiply all the numbers together and I'll solve for x. And when you solve for x, your x turns out to be, the temperature too turns out to be 604 Kelvin.
Oh man, I did not get that answer.
So we gotta fix the algebra, guys. So let's talk about the algebra more on individual basis. I could go one-on-one just in case you want to know how quick we could do this algebra. That was just a quick technique I told you. But we also have all this, the practice with ideal gas laws eventually comes down to some of the algebra that we have to be able to do.
What I did was multiply.
But the first few steps are already going to give you a lot of partial credit. I want that correctly done. I'm not going to take off all the points if you got the algebra wrong. So show me your work, with this one. I hear you. That's right. I'm not done yet. Because at the end, I need to do what, guys? Get back to Celsius. So how would I go back to Celsius from Kelvin? Subtract 273, and so that becomes 331. Oh, that sounds kind of harsh for a temperature. That's high. That's because of the pressure, 3.20 pressure, it's pretty high, it's so much pressure, things are speeding up. And if there's three things changing at the same time, guys, I'm going to have to use the equation to make sense out of it. My intuition doesn't tell me what's going to happen. It's going to be hard, but I have an idea because that's a high pressure. I'm going from point A to a pretty high pressure. And in fact, my volume is shrinking too, by half. So small volume, high pressure, that's a combination with the temperature. That's good, it's just a little special effect now.
Professor, I did liters instead of milliliters. So
Works out.
But my total was 60400.
Yeah, with sig
Yes,
fix,
with
keeping
sig
track
fix.
of sig fix.
But then if I have to, that was Kelvin, so that means I have to multiply 273. I mean, not
So
even
add or
subtract
subtract?
273.
Yeah.
So that must be considered an answer.
Yeah, I think you might have used the point 15 at the beginning for the 273, is that it? Or you just kept it 273 from the beginning?
I kept it at 273. Yeah.
So sometimes, like it's just a little bit of, like if you get a number and you cut a certain digit, so we have to be careful about sig fix from the beginning.
Okay, I just
But I want to say, let's just first, because all the answers are there, let's first practice with the plug and chug, what's needed. I want to do one more variation that's conditional.
I put the T1 and T2 on the wrong side. I think I put T2. I put the value for T2 as 302, and I saw.
Yeah, so we gotta. That's why we gotta make the mistakes now, so that at the end we get to.
I see what I did. Yeah, I got to make sure that T1 is T1 and T2.
And it's also good to kind of check it based on like what expectations we have. Because I'm shrinking the volume, I'm making a high pressure there, as far as the changes go.
It's 331 degrees Celsius.
Oh, I like this question.
Oh, because we got to use the arc constant thing?
No, this is number 8. Guys, the rest I'm leaving it up to you guys, so there's more questions for practice in between. But I want to have a chance to talk about this next question. I'll give you guys a few minutes to give me the first step. Oh, I like this one. Let's work on it. Let's make some noise with, no, not like that, you know, but just to work on the problem, right? That's good. Are you guys feeling better about this? You know, like I'm feeling good. But let's work on this. Let's see how you feel. It's not so bad. I'm just gonna disappear. You don't have to pause this one because I don't want to cut. You know, like, we'll cut it up one more time after this, so I won't give too much time. It's just too many. There's gonna be too many parts than what it is. I know it's good.
He has all the first part.
Everything was just, there was only that little.
Yeah, there was one small chunk missing, and then I started it again, and then it went for another 20 minutes or so.
And I know coordinates got the whole
Small
chunk.
chunk, yeah. I have that small chunk that he missed it already.
Okay, so can I get both uploaded?
Then both is
I don't know what I'm gonna call it. There's the one with the little small chunk missing, and then there's another one with the small
then
chunk.
both is going to be complete.
So that's gonna create another part then. So part 1 and 2, yes, just for that.
If,
If you want, I can put all the clips together and like.
Oh, you do something like that? Can you guys airdrop the whole thing to
It's
him?
gonna take a while. I can meet up with you on 10 o'clock and give you a look back.
So how long would it take? Takes how much time?
It takes a while.
Takes a while.
But there was no formula.
Or we can do separate.
I wrote everything I
ST.
Maybe it's like you have to multiply it with the different But you know why it doesn't make sense? Because the other hydrogen was the
Right, guys, we're wasting out a video time.
Wait, so standard temperature is 0 degrees Celsius? Okay.
Guys, is this conditional?
Yes.
How'd you know that? That's right. That's what it takes. Is this conditional?
Yes.
But it's not.
There's the different variables.
No, I'm not going to use the equality for it.
We need to know what STP is in order to plug in with those variables.
Is this conditional?
Yes. That's more than.
I'm gonna try it. Do it. See how it works.
Natalie, is this conditional?
Because he gave us volume in front of
Natalie?
So like the
Where's
first
Natalie? Natalie, I'll find your. Is this
Yeah.
is it the one with the missing thing? Is this conditional? How'd you know if the temperature changes?
NMHG.
So how'd you know you had a different temperature to start with? But the volume is the most clear one, right? The volume is 22.0. Can I get everybody's attention, please? Guys, I'm happy we're working on this together. But just for the sake of the video,
They're so happy.
I feel good because I know break is coming up. I'm really in a good mood.
We're trying to find it.
Guys, back there, please. Oh, this is too quiet. But yeah. So coming back to this question, and I'm glad you guys had a chance to discuss it, and I'm not to looked around. Beautiful, you guys got this one. Just for the sake of getting this down, guys, for everybody else, as a video, so we can have it with the right communication. So looking at this question, I realize it's conditional because we start with the volume that's 22 milliliters, end up with a different volume. So there's two different values for the volume. And they're also mentioning STP, yeah? And if it's a conditional problem, guys, I want them to have this mentioned. I have this for a reason. If the question is conditional for STP, I don't have to use the equality. I just go straight to what it means by the pressure and the temperature that we have for an STP. And I'm gonna write everything down. So don't write down, oh, 1 mole is 22.4 liters. No, they have already given me a volume associated with that. Remember, at STP, I don't have to have 22.4 liters. I only do if it's for 1 mole. That's a good equality, I could use it, but it's not necessary for this problem. And so when I write everything down, everything I got from the beginning, my V1 is going to be 22.0 milliliters. Guys, when I turn around, I could still hear you talk. Make sure we can get this down for somebody else who wants to watch it and get something out of it, please. Otherwise, I like the fact that we're discussing it. My P1 is going to be 1 atmosphere. Or you know what? You could also write 760 millimeters mercury. And I'll give you all those equalities. Trust me on that. If I keep it in atmospheres for 1, you could keep it, you know what? I'm going to use 760 millimeters mercury. And maybe you're wondering, okay, how did this guy get that 760 millimeters mercury? That's the pressure I got for what? STP, standard temperature and pressure. Why did I use millimeters mercury? Because eventually the question is asking me to get a pressure in millimeters mercury. Why not? Let's keep it in millimeters mercury. I could have used an atmosphere for it. But I know if it's conditional, guys, as long as I match the units, things work out. So why not, if I have the chance to just remember if I remember the value for what the pressure is at STP in units of millimeters mercury, I'll use that. Okay, what else, guys? I have T1. 0 Celsius, which is 0 Celsius, which is going to be 273 Kelvin. That's what I have initially.
Okay, so I guess I messed up because I used the 1 ATM.
It's not messing up, it's just that there's going to be an extra work.
An extra step at the end.
Extra step at the end.
Right.
We just want to speed up the process as much as possible, right?
Right, okay, so I would, in order to convert it, I would just have to multiply it by 760. 760 is 1.
Question, Omar?
No.
You want to do it on the go? You can, I mean, it's not a problem. That makes my job easier. Guys, again, just to solve these problems, I have other variations I want to make sure we could work on. I know we got excited, I'm excited too. I don't know why, but I'm excited. V2, 34.8 milliliters. Back there, what's the pressure too? Yes? I just want to check, is it a question that you guys were asking about this, or so you got it. So it's V2 is this, right? Guys, just to give a chance, please, to everybody else, if you got it, that's great. but just out of respect for other students who want to pick this up, especially if I'm going to upload this video. What about the temperature too? I also have that, 45 Celsius. Can I keep it in Celsius? No. So this is going to be out of 273. And what would I get for that part? 380? What about the moles? It's a constant. It's a constant. You know what it becomes? P1 V1 over N1 T1 is equal to a P2 V2 over N2 T2. I'm not going to use PV equals nRT for this one. The moles are constant. Did I even have to use maybe the molarity, like the equality I have at STP to find the moles to plug in? You could, but they're going to cancel out. It saves so much time, guys, using the right equation for these things. And it just becomes what? Plug and chug. Do I have the pressure one? Yes, I do. 760 millimeters mercury. Do I have my V1? Yes, it's 22.0 milliliters. It's going to cancel with the other one. Do I have the other volume? 34.8. Do I have T2? 318. Do I have T1? 273 Kelvin. And all the units canceled except for this MMHG. Is this solved for us? It's already solved for us. I just wanted to have a conversation about how to approach it. So when you solve for P2, what would you get? 560? Does that make sense? Higher temperature, the volume increases. Any other values? I don't know, because it's hard to make sense out of it because it's just.
I got 556.
You want us to round to a whole number or leave it as like one that's
Keep it based on how many, what's the list number of sig figs in all the numbers? Because we're multiplying and dividing. So if the list number of sig figs is 3, just keep it 3 for all of them, right? According to the rules for sig figs.
556 is what I got.
Anybody else for 556?
I got 556 twice. I
And
did
you
it
had
twice.
550. Oh, I'll go with 560. I'll go with the 560. We'll check that also. You know what? I can check my answer as well. You guys know that this is all solved for us already? So why are we having this video, right? I just want to have a chance to tell you the approach, the steps it takes for some of these variations. So if you go all the way to the end, oh, this is already all solved for us with my good handwriting. Right here.
560.
560.
What did I do?
It's okay, Ida. Now you're close enough. As long as the work is put together correctly, a little bit here, there. Of course, it's important, you know. I can, but I don't want you to beat yourself up too much. We could fix those. Now we're gonna move on, guys. The next question. Give me a chance to work on this question with you, but there's variations that are important here. Dinitrogen oxide, which is laughing gas, used to be used by dentists. They don't use it now. It's used by dentists as an anesthetic. If it's 20.0 liters tank of laughing gas, so if you got this many liters of laughing gas, which contains 2.86 moles of N2O, at a temperature of 23 Celsius, what would be the pressure in the tank?
They still use it.
Before we move on, is this conditional? No. Are you sure? Are you guys sure if this is this conditional?
No.
Take a look at it. Who wants to bet?
It's not.
I'm not gonna make that. It is $5. Yeah, I'll be losing, so I won't make. I'll open. So you're right. It's not conditional. It's not conditional. It's not a conditional case. How would I know that? Do you have two different values of the same variable? Do I have two different values of volume?
No.
Do I have two different values of pressure? Do I have two different values of temperature?
No.
We got 4 variables, and it's not about having two different values of any of them. So it's not conditional, right? Agreed?
So dinitrogen is the same thing as saying nitrous? Nitrous and dinitrogen. Isn't it called nitrous oxide?
No, it's similar. We'll talk about the nitrous. But I just want to make sure we get to this. I have to check myself with nitrous. I'm sorry, I don't know exactly what
One of my best friends is a dentist. We have fun sometimes.
Oh yeah? Are they still using? I thought they were
Yeah,
not
they
using
still
the
use it.
nitrogen oxide. They still
use the nitrous oxide, yeah.
and they call it nitrous oxide.
I call it nitrous.
I know it gives problems. I know one thing that it gives problems, but I'm not sure. I gotta check that also. From last time I checked, I think there was some problems with that one. And they warn you about that too. So what's the step 1? I'm gonna write everything I got. What's the step 1, guys? I'm gonna write everything I got. And it's not conditional. So which equation would you use? PV equals nRT. I would use PV is equal to nRT. Guys, there's a couple of important things that I want to tell you. First, I want to show you how easy this is. But we've got to build this up. Because this is where we start mixing in the stoichiometry. You see what I mean. So do I have your attention on this, please? So it's PV equals nRT, and actually this is tough, I know. It's late. It's almost what? 9 o'clock. Do I have the pressure? No, I'm looking for that. Do I have volume? Do I have N? Do I have temperature? Do I have R? I'll give it to you. Now, which R would you use in this case? Which R is convenient, guys, to use? 62.4 or the 0.02806?
62.4.
Why? Because they're asking me to find the pressure. They were asking me to find the pressure in units of millimeters mercury. So if I keep the R in units of millimeters mercury, it will help me find the pressure in that same unit. So as long as the units are consistent, guys, the plug and chug works out in this equation. So can I just use any units of volume if I use PV equals nRT? Can I use milliliters in this equation? No.
No.
My volume has to be in units of what? Liters. How come I was able to use milliliters in the PV, in the conditional equation, and not in here? Because the R decides what kind of units I use there. For the other equation I used, guys, as long as they're both consistent, I was good enough, except for temperature. It's got to be in Kelvin. And these are the little details in the problem solving that I wanted you guys to make sure you practice. And so in the PV equals nRT equation, I got to make sure that my volume and every other unit, guys, matches with the units of R. So if I'm going to use volume, it's got to be in liters. Why? Because R is in liters. N is moles, 2.86 moles. My R is going to be 62.4 mmHg times liters over moles and Kelvin. Because R is in liters, my volume has to be in liters. Now why did I choose to use 62.4? Because I wanted my pressure to be in millimeters mercury. So if I plug in this R, which has millimeters mercury, my pressure will end up with that unit. Or if I'm going to use a pressure that's millimeters mercury, I better use this R. So R decides what kind of units you can have for pressure. And then there's temperature. Oh, better be in units of Kelvin. And I'll promise you, if the problem is worth, I don't know, 10 points, I'll take off all 10 points, maybe more. If you do not use Kelvin. Okay, to be positive, keep it Kelvin, keep it in Kelvin, right? Keep it in units of Kelvin. So I wouldn't say do not. I know it sounds negative. Or in case of fluorine, I'm just making a commercial with fluorine again. Just keep it single bond. 296 Kelvin. It's solved for us, step by step. Can we solve for pressure? Sometimes, guys, I like to work with the variables, and I'll do the algebra with the variables before I do the plug and chug. It's your choice. Are we okay with this? Do you see how easy it is? Oh, it's just a plug and chug. But I just gotta be careful with the units. That's how I wanted like on an exam, but I thought it was a plug and chug. How come we're having a hard time working with this type of problems? We need some practice. I know, it's not easy, guys. It's easy for me to say, okay, go ahead. We have a lot of things going on. But just a couple of hours, just give it a try. And we're gonna have a chance to see each other again with these things. But I have other variations I want to talk about. So I'll leave the rest. It's already in the notes. It's so for us. I'll leave the rest for you guys to look at it. But let me do this, guys. Can I change this question? Let's change this question and discuss how everything changes. You know what I do? Instead of me giving you guys the moles, just to show you how it works, instead of me giving you the moles of N2O, I could make this change. I could give it to you in terms of, I have 5 grams of N2O. And you start thinking, okay, let me solve for this, right? So this guy gave me the grams. He didn't give me the moles.
You can convert
Now, is this
grams to
conditional? Is this conditional? No, it's not. So I'm using PV equals nRT. Let me write this down again. I know I'm using PV equals nRT, right? So I use the PV equals nRT just to emphasize this plug and chug. I'm looking for P, that's what I'm looking for. They give me V, make sure it's in units of liters if you're using this equation. These guys are giving me R, T, I'll give all that. So in the problem it's given to us. But what's missing? The moles is also missing. Should I stress about that? Not if I know my stoichiometry. So if they give me grams and they tell me this is N2O, which is nitrous oxide.
Nitrous oxide.
I'm tired. I have my skin. Right? It's can I get the mole?
Yes.
So it's still a plug and chug, but the way these problems are going to be varied, which makes it seems hard. But we need the practice so we can master this, is by including now some stoichiometry, right? Which is got to do with the moles, guys. When it comes to stoichiometry, it's about the moles now. So the only difference between this variation that I just made, and you guys can give it a thought, and the earlier case, is the fact that I didn't give you the moles directly, I gave you the mass. And there you go, I got your email. Don't worry. Right. Are we okay with this? So I got I don't have the moles, but I could find the moles. I have 5 grams of N2O. Can I change it to moles, right? For every 1 mole of these, I'm using a molar mass, guys, which is an equality. For every 1 mole of these, you look at the periodic table, that's 28.02 plus another 16, we get 34.44. 0.02 grams for every 1 mole. So grams cancel. Do I get the moles now? And if I get the moles, can I plug it into this equation? Can I solve for the pressure now? Do you guys see what I mean? Or what kind of variations do I get when I have to use PV equals nRT? It's not going to be as straightforward as, okay, you just do the plug and chug just with that. I'm going to include some stoichiometry. You'll see it on the sample exam. And it's also a good review, guys. For the 3rd exam, I know it's going to be, we're going to work on that, but it's also a good review for the final exam that's coming up. I'm also worried about that. So practicing these variations at this point in time it's also helping you go back and think about the variations we've seen before with stoichiometry that needs to be included. And so, let me give you guys a question to think about. Worth thinking about. And some of these variations that I just talked about, guys, what I just made a change for, there's a problem which has it exactly that I might ask you, how many grams of oxygen are in a cylinder that has this and that? If you want to find grams, what is it that you need first? Mole. Can you use PV equals nRT to get the mole? How do I know I'm using PV equals nRT? These guys are measuring temperature, volume, pressure, not conditional. I could use PV equals nRT, get the moles of oxygen, change the moles of oxygen to, these are the variations I have for you for practice. Have I solved it for you? So sorry I'm going about this fast. Again, I'm introducing to what you guys need to practice now.
It's the
Is this helping?
non-conditional
Let me
ones.
know. I'm just talking now.
Non-conditional ones are very straightforward about what you need because it's just saying you have this and this and this. What's here? It doesn't really say that anything's
Agreed.
gonna
Agreed.
change.
Agreed. I like this one. I have other ones that I've put, but I like number 6. Oh, give this a try. I would work with this one with you guys. So give number 6 a try. We have the last 20 minutes. I want to give this a start. And then for all the other variations, everything is there, guys. You would work on it. And on Monday, for the first 20 minutes, I'll have a little more time with you guys. I hope this video, when you go back to it, it helps. This is a good one. It's worth really thinking about. There goes a question. Now, with every question we approach for ideal gas laws, what's the first thing I got to think about? Conditional or not? Is this conditional? No, it's not. I don't have two different values for a given variable. I know it's not conditional, so I'm going to be working either with PV equals nRT or pressure times molar mass is equal to dRT. But that's out of the question because there's no need for density here. And so when I work with this question, first, I got to really see what's given to me. I don't know what's given to me in this question. So I'm going to try to figure that out because there's a lot of information now. So let's just bring this back. Oh, no.
We got 500 milliliters of air.
Oh, I forgot there's a challenge there. GCC. Is this better?
Yeah.
Things are gonna go up, I know. Please hold. Okay. So I got the problem. I want to write down all the variables first. And I don't have the solution for this one, so we have to solve this one. These guys are giving me the volume of carbon dioxide, which happens to be 4.1% of the 500 milliliters, which is roughly the volume that our lung is going to hold. So the amount of carbon dioxide is 4.1% of that. So the volume that's given to me for carbon dioxide is going to be 4.1%, which is 4.1 out of 100. That's what a percentage is. A ratio out of 100 times the 500 milliliters. So the volume that I have,
20.5.
20.5, is 20.5 what, guys? Milliliters. But since this is not a conditional problem, eventually when I use PV equals nRT, I need to have my volume in what units? Liters. So in PV equals nRT, R decides what kind of units we need for the volume. Right, Ani? And so we need to have the units in liters. So for 1 liter, we have 1,000 milliliters. We convert, and so we have 0.0205 liters. That's my volume. I don't know where I'm going yet, but I did decide that this is not conditional, and I'm going to write down what I have. What else did they tell me, guys? And there's 2 ways of solving this problem. I want to mention both ways of solving it. We just don't have enough time. If you guys can stick around just a little longer, we'll do it. So they're saying STP. What does that mean?
Standard temperature pressure.
Standard temperature and pressure. So one way of solving it is to write down what I know about the standard temperature and pressure. And so the standard temperature is 0 Celsius, which is 273 Kelvin. And my pressure is what, guys? 1 atmosphere, or 760 millimeters mercury. If I don't have to use the 760, guys, I'll use the 1 atmosphere. It's an easier number to deal with in my calculator. And having all this information, I mean, this is all I got. I know where the question is going. The question is saying, eventually, you know, how much of this KO2 solid, and KO2 is a solid, so I can't use PV equals nRT for KO2. Everything I got is for carbon dioxide in my lung at STP. I know the volume is 4.1% of the 500 milliliters, and I think that was kind of challenging in this problem to start with, right? To realize that. Usually, guys, I'll just give you the volume, so I'm not going to go through this extra step, but this is good practice. Yes? I don't have to. You could use millimeters mercury. That means you have to use the appropriate R constant for it.
So we're gonna use the R that correlates with
We have 2
ATM.
different R constant values for it. So it really depends on which R constant. I like to keep it as atmospheres because it's an easier number to work. But if you're referring to the previous problem we did, in the previous problem, because they were asking me to find the pressure in millimeters mercury, it was convenient to have it all in millimeters mercury to start with. But usually, atmospheres, in my equations, 1 atmosphere is an easy number to deal with. So this is not conditional, which means I'm going to be using PV is equal to N R, and the R I'm going to be using is 0.08206 atmospheres times liters over Kelvin and mole times T. Now if I use this R, that means my pressure better be in what units, guys? Atmospheres. I chose this because I want to use atmospheres for my pressure. If I choose 62.4, then I would have picked millimeters mercury for my pressure. So R decides what kind of units for pressure, volume. That's why in PV equals nRT, guys, I'm locked into whatever the units of R is. R tells me what kind of units I can or cannot use. But temperature is always Kelvin.
We picked ATM because
It's just an easy number.
and it didn't tell
At
us that we had to use.
Yeah, I mean at STP, this is talking
millimeters.
STP. Sorry, I'm hurrying through this. They're talking STP, and at STP I'm either gonna have this as 1 atmosphere, nice,
Or 760.
or 760.
Right.
You don't mind being in the video there, like it's gonna go to the future generations. Are we okay with this one? Right? So look at, what do I have that I could use in this whole PV equals nRT? Do I have the pressure? Yeah.
Yes.
We definitely have the pressure. We have an exam coming up. So we have, do I have the volume? Do I have the moles? And this is all about carbon dioxide, by the way. Do I have the moles?
We don't have the moles. That's
No,
the one. That's the only.
That's
thing
the
we
one
don't
I'm looking for. Do I have my temperature?
Yes.
Yes. Can I do the plug and chop to find the moles? Oh yeah. That's it. I was an evil laugh for my part. Yeah. So I'm gonna plug it in. 1 atmosphere. I know it's late, guys. It's late. 0.0205 liters. I got the moles. 0.08206. Atmospheres, liters, Kelvin, mole. You don't have to show the units all the time. We could see, sorry, how the liters cancels, the atmospheres cancels, You could prove this there on, and then we got the temperature. What's the temperature? 273 Kelvin. Can I now solve for what the moles are from this equation? I need your help. I don't have much time, and you have a calculator. I have a calculator too, actually. I have my phone.
20.5 divided by 22.4. Yeah, I got 0.915. I'm just gonna stop there. At 3.
0.009.
That's not what I got. I got 0.915. But things go wrong with me a lot.
I'm getting confused already with
What's
different.
that equation? We're looking for the KCO2, right, professor?
So if I solve for moles from that equation, guys, if I solve for moles, we get 0.000951 moles of what? Carbon dioxide. Agreed?
No, I need.
We'll check the algebra to get it right. Again, I'm in a hurry with this. Am I done with this?
No.
So I use PV equals nRT, and if you're using PV equals nRT, it's going to give me information about the gas. And this is a step a lot of times on an exam I see missing, because you get the moles for the gas, but we got some stoichiometry to be done, right? So once you have the moles, it's back to where we were before on the second exam. Can we do some stoichiometry? If I have the moles of carbon dioxide, do I have the coefficients to go from moles of carbon dioxide to the moles of KO2?
Yes.
And we do that, guys, stick around, because we're going to do another way of solving this problem. So once you have the moles of carbon dioxide, can I get to the moles of KO2?
Yes.
This is going to be 4 moles of KO2 for every 2 moles of carbon dioxide. So that cancels. Can I go from the moles of KO2 to the grams of KO2 now?
Yes.
How would I do that?
Periodic table.
Use the molar mass. Anybody get the molar mass for this? 71.1 grams for every 1 mole of K2O, no, KO2. That cancels, and we get information about the grams of KO2. There goes one solution. So it's not so bad, right? Guys, if you just give me an extra minute, you guys want to do this faster? I didn't have to use PV equals NR.
Really?
There's a part 4 now. So we're going to continue with part 4. That was a little break.
I think I know what
It's okay. There is another way of solving this, guys, and this is what I mean. If it's already an STP, and if it's not conditional, you guys remember that 1 mole is 22.4 liters? You guys remember that? Isn't that an equality? Well, you guys did very well on your first exam. I remember. I was proud of that. And so, if I have the moles of the carbon dioxide gas, can I figure out the mole, if I have the liters, can I get the mole?
Yeah.
Oh, I already know that this is 44.1%, so we had this in the video number 3, we solved it. It's going to be too many videos now to upload. Right, so I could now multiply this by 1 mole over 22.4 liters, and everything, guys, it's a faster step. This is why at the very beginning I said it's good to know this equality if the question mentions STP. I have every question that I pick, guys, is going to teach us something here. Every question that you guys work on in this homework, I've picked so it could teach us something. Both for my Chem 101 and Chem 110. In fact, I have the same set of questions for both of them, for practice.
Oh, that's funny.
But I'm gonna crank up the level for Chem 101 a little bit on an exam.
22.4 is what I end up dividing the...
Eventually in the algebra, yeah, it works out. That's why.
Because I figured out what I did wrong was I forgot about I wrote it on the paper, but when I plugged it into the calculator, I didn't convert the milliliters to liters.
And the rest is just the same.